Welcome to this video on continuous probability distributions and the normal distribution. After watching this video, you will be able to list at least 3 differences between discrete and continuous probability distributions, explain why in a continuous probability distribution, the probability of a single value is 0, define the term probability density function, list the 2 requirements of probability density functions, calculate the probability of an event using a uniform distribution, and lastly, list the properties of a normal distribution. Discrete versus continuous probability distributions. In the previous section, we studied discrete probability distributions. In this section, we will be learning about continuous probability distributions. What are the main differences between discrete and continuous probability distributions? Discrete probability distributions. The probability of one particular value, for example, x equals 2, is going to be a value between 0 and 1. The sum of the probabilities is 1. Discrete probability distributions, when we graph them, look something like this. We can also express a discrete probability distribution as a table, such as the one shown here. How does this compare to continuous probability distributions? Let's see. Well, when we graph continuous probability distributions, they might look something like this or like this. Notice that we have, instead of these single bars at discrete values, we have a smooth continuous curve, which may or may not be symmetric. One interesting thing to note that's very different for continuous probability distributions is that the probability of any single value on this graph is always going to be 0. And we'll explain that in a little bit more detail in the coming slides. To find a meaningful probability, we have to actually look at an interval or a range of values. In other words, we have to look at an inequality for our random variable instead of an equality like we see here. Additionally, it's impossible to create a table like we have for discrete probability distributions because there are an infinite number of possible values that our continuous random variable could assume. Why is the probability of a single value 0 for continuous probability distributions? The classical definition of probability states the following. The probability of an event is equal to the number of ways that it can occur divided by the number of possible outcomes. Since we are working with a continuous random variable, there are an infinite number of possible outcomes, rendering the probability of any particular outcome 0. We say that the real number line is dense, which means that there are an infinite number of values between any 2 points on the number line. For example, just looking at values between the numbers 0 and 1. We could have 0.1 or 0.11, 0.111, etc. Since we do not place a limit on the number of digits after the decimal point, there are an infinite number of values between any 2 points on the real number line. Another way to explain the fact that the probability of a single value is 0 is to think about the area under the curve. The area under the curve is equal to the probability of an event occurring. The probability of a single value can be represented graphically as a rectangle with a height of h and a width of 0. Since the width is 0, the area is the height, h, times 0, so the total area of this rectangle would be 0. Probability density functions. When working with discrete random variables, we create discrete probability distributions in either graphical or table form to express the probability of a certain event. When working with continuous random variables, we use probability density functions to compute the probability of events. All probability density functions must share the following 2 requirements. Number 1, the area under the curve must equal 1. Number 2, the height of the graph must be non-negative for all possible values of the random variable. The area under the curve of a probability density function over an interval is equal to the probability of observing a value in that interval. The uniform distribution, a way to understand probability density functions. Suppose you are waiting for the plumber to arrive at your house to fix a leaky pipe. The plumbing company gives you a 4-hour window during which the service professional will arrive. We will assume any time within the 4-hour window is equally likely, and we will assume, unlike in real life, there is a 100% probability that the plumber will arrive within this 4-hour window. Let's graph this probability density function. The graph will look like a rectangle. Notice that the graph is flat because the probability of the plumber arriving any time within the window is the same as any other time, as far as we know. Now we need to know what value should go right here on the graph and what value should go right here. Well, we know that this value on the x-axis, which is measuring the time in hours, should be 4 because we have a 4-hour window. What about the value on the y-axis? How do we know what that probability should be? Well, we know that the area of this rectangle in here, this region in here, has to equal 1. We know the area of a rectangle is length times height. So we have the area of 1, right? Because remember the area is a probability. It's 100% or 1. So we have 1 is equal to the width, 4, times the height right here, which is our question mark. So if we just use a little bit of algebra and divide both sides by 4, we find out that the height of this graph is 1/4. So now we have our uniform graph, and so we can actually start answering questions about the probability of the plumber arriving in different intervals. So let's go ahead and do that. What is the probability that the plumber arrives within the first hour? Let's represent that on our graph. As you can see here, I've used a purple region to shade between 0 and 1 hour. So what we need to do is we need to calculate the area of this purple box. So remember the area is length times height. So we have 1, that's the length of the rectangle, and the height is 1/4. So 1 times 1/4 is 1/4, which we could also express as 0.25 or 25%. What is the probability that the plumber arrives between the first and third hour? So now notice we have a new rectangle that's shaded from 1 to 3, and of course it has the same height of 1/4. So again, remember the area of this purple rectangle is going to be the probability of this event. Again, we have the area of the rectangle is length times height. This time, notice, however, to figure out this length, we need to do a little bit of math. We could really easily just count the number of tick marks, right? We could say 1 tick mark, 2 tick marks, and just say 2. Or if you wanted to think about it another way, you could think of it as this number 3 minus 1. So either way, we get 2 times the height of 1/4, which gives us 1/2. So there is a 0.5 or 50% chance that the plumber arrives in this shaded window. What is the probability that the plumber arrives during the last half hour? So again, we shade the last half hour here. Notice that this area is smaller than some of the other rectangles that we've looked at. So again, finding the area of this rectangle, the length, this horizontal distance, is only half an hour. It's 1/2. So that's why 1/2 is here. And if you wanted to do the math, it would be 4 minus 3.5. And again, the height is still 1/4, so we have 0.5 times 1/4, and that gives us 0.125, or about 12.5%. So at this point, you might be asking yourself, why are we bothering doing problems using a uniform distribution? After all, the title of this video said nothing about uniform distributions. It said something about the normal distribution. And the answer is that the uniform distribution really helps us to internalize this concept that the area under the curve is equal to the probability of an event occurring. So here's the uniform distribution, and we just did a few examples with that. But we really want to get, and what we really want to work with is this normal distribution. So why spend time on something that looks like this when we don't even really care about uniform distributions, and in real life, most things are not uniformly distributed? Well, the very simple answer is that the math used to calculate the area under the curve, when your curve is a flat line, is very simple. You can just use the area of the rectangle, length times width, and so the math just boils down to basic arithmetic. Unfortunately, the normal distribution is characterized by this function right here, and in order to find the area under the curve within a certain interval, you have to use integral calculus. Fortunately for us, we can also use technology, which is what we will be doing in this class. So here you can see we have the normal distribution, and superimposed on the normal distribution are some percents that show how the data is distributed. So if you recall, this is called the empirical rule. It's also sometimes called the 65, 95, 99.7 rule. And again, these are approximations of the area under the curve. Keep in mind that all of these values are approximations. And to avoid errors, we are going to be using technology to find the area under the curve. If you want a more thorough review of the empirical rule, please go back and watch that video. Properties of the normal distribution. The normal distribution is centered around the mean of the data. The mean, median, and mode are all equivalent for data that is normally distributed. The normal curve is unimodal and symmetric. Because of its symmetry, the area under the curve to the left of the mean, this half, is exactly 1/2, and the area under the curve to the right of the mean, or to the right of center, is also 1/2. The normal curve extends infinitely in both directions. As the random variable x on the horizontal axis approaches positive or negative infinity, the normal curve approaches but never touches the horizontal axis. This is called a horizontal asymptote. The shape of the normal distribution. Notice that the bell shape may be stretched out or compressed depending on the size of the standard deviation. If we look at this graph over here, we can see that when the standard deviation is 0, all of our data is clustered at 0, and it does not exist anywhere else. As our standard deviation becomes non-zero, we have a very tall, very thin curve. But as our standard deviation increases, what's happening to this curve? Notice that it's getting flatter and it's getting wider. So the bigger your standard deviation is, the shorter and wider your curve will be. And the smaller your standard deviation is, the thinner or narrower and taller your standard deviation will be. But no matter what, the area under the curve, regardless of its overall shape, will always be 1. You should now be able to list at least 3 differences between discrete and continuous probability distributions. Explain why, in a continuous probability distribution, the probability of a single value is 0. Define the term probability density function. List 2 requirements of probability density functions. Calculate the probability of an event using a uniform distribution, and list the properties of the normal distribution.